Welcome back. So last time, what I did was essentially focus on the k equals to 1 theory, say why that's special, and show that there is a hybrid formalism in which it's described by a PSU 1,1/2 level 1 Weissimino-Witten model. And moreover, that model has a free field realization, which enables one to compute its partition function, the set of physical states very explicitly, and including the spectrally flowed states. And so this is what we essentially did in the last lecture. We had 3 different pieces, namely the piece corresponding to the PSU 1,1/2. So these were essentially 4 bosons, 4 fermions and 2 bosons, because we had to coset by essentially the 2 U1s. So you have only, out of the 4 bosons, you effectively have only 2 bosonic degrees of freedom. And this was the effect of the spectral flow, and the W dependence, the W labeled the spectral flow state. The others were more familiar pieces. This is the piece of the twisted T4. And then there was a ghost piece, which consists again of 2 bosons and 4 fermions. But with the opposite statistics. So, the bosons were from the diffeomorphism coast, and the fermions were from this other coast, which is essentially like super diffeomorphisms. So one of the important things which I was mentioning last time is that the ghost piece cancels exactly with the non-zero modes of the ADS3 times S3, because there were 4 bosons and 4 fermions and 2 bosons, and the ghosts were also essentially 2 bosons and 4 fermions, but opposite. And so these two cancel with each other, and you're left with the 0 mode piece, which is very important, which carries the information about the spectrally flowed sectors. And so that was this, and then there's the T4 partition function, which was the standard twisted T4 partition function. This was the contribution for any given sector W, and of course the full partition function, you sum over all of them. I just want to make one remark here, which I want to emphasize, that this is very different from the k greater than 1 picture, even in this hybrid formulation, because actually you can see that from the hybrid formulation that for k greater than 1, and certainly for large k, effectively you get 6 bosons from this SL2R and SU2 pieces, and there are 8 fermions. So you can see that from the group. Also, I mentioned there's the bosonic group, the SU1,1, and there's the SU2. So that's 6 bosonic degrees of freedom once you have coseted by the U1s. And then there are 8 fermionic degrees of freedom, which are the off-diagonal ones. And so when you cancel with the ghosts, remember there were 2 bosons and 4 fermions that you cancel. So you're left with 4 bosons and 4 fermions after the ghosts cancel. So this is what you normally have for k greater than 1. But here, the k equals to 1 theory, the PSU 1,1/2 had only 4 fermions and 2 bosons, so it completely canceled except for the 0 modes against the ghosts. And this is why, in some sense, I was saying it's topological, that there are essentially only these 0 modes left from the ADS3 times S3. The spectrum of states is vastly smaller at k equals to 1 compared to k greater than 1. So for k greater than 1, you have 4 bosons and 4 fermions from the PSU 1,1/2 after cancellation with the ghosts, and the T4 gives you again 4 bosons and 4 fermions. So totally you get 8 bosons and 8 fermions in that case, which is what you normally would expect for a 10-dimensional critical string theory. But here we have instead only the T4 piece. So we have 4 boson and 4 fermion as the physical degrees of freedom. So it's much less than k greater than 1. Then we impose the Virasoro condition, because this was just the, if you wish, the generating function of all the states. But if you have to look at the on-shell states, then you impose this. And one way to do that, which I went through probably a little fast, was to look at the contribution in this. If so, all the non-zero oscillators come from here. So if there's a piece which is Q to some power H oscillator inside this, then you know that the on-shell condition basically tells you that the power of Q and Q bar are 0, and that's this condition. You get Q to the H oscillator from here, and then there's this piece, which is this one. And so you can use this to solve for M, because there's a sum over M. So this essentially tells you that the value of M is fixed. M is the J30 quantum number. And now, if you look at the on-shell partition function, so essentially the Q power goes away, but the net power of Q is 0, but the power of X, this X to the M, because M is this, so X to the M you can replace by X to the W by 2 times H oscillator by W. So if in effect the generating function is just the same as the what you had, but now the tau is replaced by T over W because of this 1 over W factor over here. You get a T over W. And then there's an additional condition, which is sort of like a level matching condition, which tells you that the lambda and the lambda bar are essentially the same up to an integer. This is the statement that the left and right moving J30 in space-time differ by an integer. So that tells you that basically the oscillator levels on both sides should be 0 mod W. And that's what is indicated by this prime over here. So and then using some theta function identities, you can rewrite it as a sum over the full partition function. You can rewrite it as a piece involving the even sector and the odd sector. And one of them looks like a Ramond sector and the other like an NS sector, and namely that it's given in terms of this theta 2. The Ramond sector is what we had written here, the answer written over here. This ZR is that piece, this piece, but now you also have a piece involving the theta 3, if you write it in this way. So this is a convenient way to write it and compare it with now the symmetric orbifold CFT. And so this is what I will now compare and argue that the symmetric orbifold CFT is identical to this, that the full spectrum of states of the symmetric orbifold, which we should compare with the string perturbative string answer, is given by this. So are there any questions at this stage?
I have very, very basic question, like a
Sure.
technical question. So
Yeah.
in the usual, when we work on this flat string theory on the flat space, we usually start with the light quantization. For this ADS3, is there also such a light quantization? And you also have like a Virasoro constraint and level match condition there? Or
I mean, people I think the light cone gauge is a very difficult, a little tricky gauge to impose an ADS3 because there's no uniform, the metric, because there's a warp factor. So it's a little difficult to impose a light cone gauge. There is an analog of this called some kappa light cone gauge that Metsav and Cyclin and others have try to use, but it's still very difficult to quantize in that gauge beyond some large radius limit. So of course, in ADS3, the way I was doing it, or what I reviewed of Maldacena and Oguri, is a more covariant gauge. I mean, it's like the old covariant quantization. And the old covariant quantization, you impose the Virasoro constraints and you get the physical spectrum. So this is essentially what we have also done here, followed here, but now in the language of the free fields. There is a BRST quantization also that you can do, that Berkowitz, Waffa, and Witten have outlined. That's more complicated, and it's I mean, actually, we are trying to understand that better as an alternative way to obtain the physical spectrum and the partition function. But it is a very complicated machinery you have to use for the BRST quantization. Only there might be some simplifications in the k equals to 1 limit, but that's what we are trying to figure out right now. So yeah, but everything that I've done is sort of the analog of old covariant quantization in Polchinski's terminology.
Okay. Okay, thank you.
Okay, so so let's compare this with the spectrum of states of the free orbifold, at the free orbifold point. Like I said, there's a moduli space, but we'll work at the point where you're sitting at the orbifold. So like in any orbifold CFT, so the first thing you need to know is that in an orbifold CFT, the states are classified by the conjugacy classes of the orbifold group, in this case, the symmetric group. So that's what we have. And what are these conjugacy classes? For the symmetric group, these are labeled by partitions of n. They correspond to the decomposing any random permutation into cycles of different length. So you can think of it as cycles of length 1, cycles of length 2. There will be n1 of them, n2 of them, so on and so forth, up to cycles of length n, the maximum number, with the constraint that summation of k times nk, if k equals to 1 to n, the total cycle length, of course, has to be equal to n. So that's those are the partitions of n that you have with subject to, so that's how you would be partitioning n. So it's of course a very big, so there are many sectors, many twisted sectors, which are all labeled by these conjugacy classes, but it becomes much simpler if you focus on, so this corresponds to the full Fock space. The full multi-particle Fock space. In fact, in the large n limit, so the statement I made in the previous para is true for generic n, but if you go to large n, then this can be viewed as the multi-particle Fock space of non-interacting. These are non or weakly interacting single particle states. Sort of exponentiated in the usual way that you do for going from a going from single particle states to multi-particle states. So at n equals to infinity, they are non-interacting, and for large n, they are weakly interacting. So this is something that people realized, that the symmetric group, you can classify all the states as a Fock space at large n. And so what we need to compare are the single particle states, because that's what the perturbative string spectrum that I just wrote for you over here. This is giving you the set of single particle string states. So we need to compare with the single particle states, the string spectrum, the perturbative string spectrum with because again, we are working on the string theory side also at G string very small. So we need to compare the string spectrum with single particle states of the CFT to the dual, the symmetric orbifold CFT. Okay, so now that's where I need to invoke some statement that may be familiar to some of you, that the single particle states in a symmetric orbifold CFT correspond to single cycles states. So what do I mean? These are states in the conjugacy class where I have one cycle of length W and the rest are trivial cycles. So this partition where I have one cycle of length W. Of length W, which can be greater than 0. So this is the analog of the single trace operators in Yang-Mills. So the multi-particle states are essentially formed by taking so a general state in this kind of a sector can be viewed as sort of multi-particle states built from single cycle states of this kind, tensor products of single particle states. So at large n, they are non-interacting. There's a 1/n suppression in the 3-point function, for instance, in the OPE. So multi-particle or multi-cycle states are suppressed. So what do we therefore need to compare? We need to compare with these single cycle states. Now, these single cycle states are relatively easy to write down. And so in fact, I've used the same letter W to indicate, because I will be anticipating the fact that it will be the same W that will correspond to this W over here. We have the spectral flow index W in the string theory, and I will claim that in this match, you will match sector by sector. So the W spectrally flowed sector will match to the W twisted cycle sector of the orbifold. So I will loosely refer to the single cycle state as the W twisted sector, because it's a cycle of length W. Okay, so
can you remind me of one thing? So this is related to the K-1. So I mean,
no, this is true for any, well, I mean, what I said so far about the orbifold is a general statement about the symmetric orbifold. It has nothing to do with the K = 1 theory. Yes, but when you're comparing this spectrum, this will be what matches with the W spectrally flowed sector of the k=1 theory.
So there is only a long string. There is no short string, or
there are no, well, you can have, of course, W=1, which is the untwisted sector, which is there in the other side also. Yeah, so there will be W=1, 2, 3. There will be long strings which are of different length W. So in the k=1 theory, this is all that we had. In fact, so this is what we had over here. So now we just have, we will compare exactly those states with the W cycle states here.
Okay.
So what I want to claim is that, in fact, this generating function that we had over here, this is exactly the orbifold generating function of the single cycle states. And I won't go into a detailed proof, which you can see in our paper, but in our, actually in an earlier paper with Matthias and I, we had written, and this is spelled out, but just to give you a rough idea, so the W cycle, the W twisted sector of the T4 orbifold, so that means T4 to the n mod Sn, can be viewed as taking W copies of T4 with which are, I should say, maybe which are sewn together to form kind of a excitation So again, I'm using this sort of long string language of the symmetric orbifold, that you consider W copies of these and sort of sew them together by some roots of unity. And you get one longer one T4, which is built out of these W copies. And it's a sort of a string of length W. So its modes are in units of 1/W. So you can think of, so there's now a fractional moding because of this string of length W. And so it's essentially the T4 partition function with moding 1/W and the orbifold invariance condition which is that the whole thing, even though it's moded by 1/W, the net moding must be equal to 0 mod W, so as to be single valued. So this is sort of the orbifold invariance condition. So you consider a twisted sector and then project onto the invariant states, orbifold invariant states. So that's what this is. And this is, if you see, And if you look at how the zero modes work and everything, this is exactly what you have over here. And you get, depending on whether W is even or odd, you will get being either in the Ramond sector or in the Nebel-Schwarz sector, because that's how the modes are quantized, and you will get exactly this partition function. So you see, this is a single T4. It's that of a single T4, but except that the mode numbers are sort of down this thing by 1/W. So the answer that we had earlier precisely reproduces the spectrum of the symmetric orbifold on both sides. I just want to make a couple of additional remarks over here that so firstly, it's a perfect match of all states in the perturbative limit.
Oh, can you remind me of the definition of T in the partition generating function?
T?
Yeah, T over omega.
T is the chemical potential of the in the space-time. So it's you can think of it as the space-time L0 chemical potential, because you see X. This was X was e to the 2 pi I t, which is the chemical potential for J30, but J30 is equal to L0 space-time. Remember the space-time L0. So essentially, this are the space-time. And now when you go to the dual CFT, that means essentially this is the space-time L0 quantum numbers. That's why I was talking here. That's why the match is exactly of the moding with respect to the space-time T. Space-time L0, and this is sort of the space-time, the condition that L0 minus L0 bar on the dual symmetric orbifold CFT, the space-time L0 minus space-time L0 bar is 0 mod W. Yeah, so exactly.
So there was also Z. Sorry, I mean, I already confused. So X and the T is related to the space-time, but this Z is now worth some chemical potential, or
sorry, no, X is e to the 2 pi I t.
No, but the Z in this argument.
Oh, the Z was that's the K30. That's the SU2 quantum number, which of course also there is an SU2 quantum number in the T4 orbifold CFT as well. So from the space-time, so from the string theory point of view, this was one of the S3 quantum numbers. But from the space-time orbifold point of view, the symmetric orbifold point of view, it is part of the SU2 R symmetry of the T4 theory. And that's the chemical potential. So in fact, that's exactly how it appears here as the chemical potential of the SU2. Yeah, so this theta function that you have over here, that Z is measuring exactly what you would do in the orbifold CFT.
Okay, thank you.
Actually, so may I ask also about this identification of omega?
Of W, yeah.
It was some kind of wrapping number on the boundary of ADS3 as far as
yes.
How can you then identify it with this cycle length on the CFT?
Yeah, so that's a good question, and maybe it will become more clear by the end of the lecture. But essentially, something that is wrapping around W times, you can think of it. So what is the twisted sector in the orbifold CFT? That's also something where you take W copies of the single T4 and kind of glue them all together. So effectively, what you're doing is you can think of each copy as wrapping a single time, and this W times is wrapping. The W cycle twisted sector is essentially something where you're wrapping W times. Another way to say it, well, it will become a little more clear, but when you look at the ground state of the W twisted sector in the orbifold CFT, then locally it behaves like there's a branch point of order W. And so that's exactly what you have in the dual, in the string theory, where you have a wrapping of order W. But this may become a little clearer when I give a little more geometric picture later. But indeed, that's very crucial, this identification of the W cycle twisted sector with the W spectrally flowed sector. And they will correspond exactly to the same thing, that it's a W sheeted cover.
I see. And so can you also introduce the N? N was the number of D1 brane, right?
Yeah, N is something we are taking to infinity. So 1 over N will be essentially, so 1 over N is like G string square, and that we are taking to 0. So everything I'm saying is sort of in the perturbative limit, and in fact, many of the things I'm saying are strictly true for the genus 0, but there have been generalizations, including the 1 over N corrections by Lawrence Eberhardt and others who have looked at the full generating spectrum. And this is actually related to something that Jungi was also wanting to hear in these lectures, but I don't think we'll now have the time, about the black holes. But maybe I'll just make some comments here, that if you look at finite N and look at the symmetric orbifold generating function at finite N, that's going beyond the perturbation theory. And in fact, you can consider sort of a grand canonical ensemble where you introduce a chemical potential dual to N. And look at this generating function. And what Lawrence observes is that if you that this full answer, which contains, if you wish, the grand canonical, is a kind of a convenient way to package the whole string spectrum. This contains also not only the perturbative string states, but even like the black hole states, or some of the other. So you know, in ADS3 there is a thermal ADS3, but then there's also, that's one background, but there is another background which is the BTZ black hole, and there are various images of it, PQ images of that BTZ black hole, and there are other geometries like conical defects, etc. So at least what for a large class of these geometries, what Lawrence shows is that if you fix the boundary to be a torus, then all the different ways of filling in the torus is included in this grand canonical partition function, that it includes all these states. So in some way, once you specify the asymptotic geometry, the string partition function, the full non-perturbative string partition function, includes all the geometries that are there. So you don't have to separately sum over saddle points. Any one saddle point, so to say, you can start with, and if you complete it, it will contain all the other saddle points. So this is something that's, I think, a very interesting observation about this large N limit. And I think, yeah, it's something people are, I think, that gives you some guide to whether, you know, you should sum over wormhole geometries and other things in these sum over in the string path integral. So at least in this highly stringy tensionless limit regime of this special ADS3 CFT2 story, you seem to have a very interesting answer, which is that you don't need to sum over all the geometries. They're all automatically included in the, so if I just start with the original ADS background, or if I start with any other background, they're kind of all related.
I see. Well, thank you. Very interesting.
Yeah, sorry, that was it went into other things. But coming back to this was also more to address Jungi's interest in that sort of topic. But we'll please ask me this question again about the relation between the W on both sides after I say more about the covering maps and similar story for the.
Can I just ask a question?
Yes.
So for I have a bit of a problem in understanding about this finite n case after for which we get these non-perturbative states. So because for first, when we discussed, I think during the first lecture, we said that n has to be, we are always in the tensionless limit of the string, so that the D1, D5 range can be thought of as F1 NS5 system. So
yeah.
So this should not work for a finite n, right? So this should not give us
Well,
a non.
yeah, I mean, so well, it's a question of all I was saying was that this is the limit where we have most control, and we are able to compare with the dual string theory, because we know how to do perturbative string theory, so we can compare the symmetric orbifold with the dual CFT in this regime. But so in this regime, you can make the comparisons like I just did, which is all in the n equals to infinity limit. But you can then be a little more bold and say that, well, if it agrees perturbatively in 1 over n, then maybe and that's the view one typically takes, that the gauge theory, namely the dual symmetric orbifold CFT, gives a definition of the non-perturbative string theory at finite string coupling also. So in some ways, we don't have an independent definition of the string theory non-perturbatively yet, but this could serve as a provisional definition of the non-perturbative string theory, and then you can ask what consequences does that have. So it is in that spirit, I think, that Lawrence is making these observations.
Okay, thank you.
I have a question. So,
yeah.
so you're considering tensionless limit and the large n limit?
Yes.
So can you say anything about small lambda case in this component theory side, CFT2 side? How that changes?
You mean if you add a small deformation, go away from the free point?
I mean not exact tensionless limit, but a small,
Yeah, so that's what you
is a small but non-zero.
But non-zero, yeah. So you perturb away from this tensionless limit. Yeah, so that's an interesting question, and it has not been, I think, addressed quantitatively. I think it should be, and I think, but there is a very definite procedure to address this question. Namely, you have the spectrum, as I said, matches on both sides, and in fact, I was going to write this, that the W equals to 1 sector is the untwisted sector. So that contains the moduli, that contains some of the moduli, contains 16 of the moduli, marginal deformations. So these are actually a little bit boring deformations. They don't really take you away from the tensionless limit. They kind of deform the T4. They are kind of shape modulus of the T4. So that's maybe not so interesting. But the W equals to 2 sector, that's the Z2 twisted sector. This contains 4 of the remaining 4 marginal deformations. And this has the interest, including the deformation away from the orbifold. So this would be the analog of the of this the 't Hooft coupling parameter, I mean, the deformation of small lambda. So you can, so this is matches, of course, as I just said, this is part of the spectrum on both sides. So you can imagine turning this on in the CFT, and correspondingly in the world sheet also, we can imagine turning on the marginal operator, which is in this the W equals to 2 spectrally flowed sector. And it would be very interesting to compare what you get on both sides. I think that's that would be you would have to compute now correlation functions, and I will be talking now about correlation functions, and we'll see how correlation functions, at least around lambda equals to 0, agree. So once you know the correlation functions, you can try to do a perturbation theory expansion in this. And
so for example, this 2-point correlation function,
3-point or even 2-point correlation function, which is what
dimensional conformal dimension should be somehow modified by
exactly. So that should be captured already in 3-point and 4-point correlation functions.
2-point, even 2-point function has a conformal dimension.
No, so 2-point function of the deformed theory, which is the same as a 3-point function or a 4-point function of the undeformed theory. So
yeah, that's right. Perturbatively, you mean?
Yeah, exactly, imperturbatively. So that's, so we know how to compute, and I will just be describing how to compute the correlation functions in the unperturbed theory. And so you can think of turning on this marginal deformation perturbatively and compute the 2-point function of the deformed theory by in perturbation expansion.
I see. So a higher point correlation function of undeformed theory can be computed.
Yes, yes. And that's
okay.
what I will be talking about, yes. So, okay, so that's, we can look at these deformations also. In fact, that's an interesting, but let me actually, since this question was asked, let me point to another deformation, which is also interesting, which also you could view as a kind of analog of the 't Hooft coupling deformation, which is to turn on Ramond-Ramond flux. So you can turn on an infinitesimal amount of Ramond-Ramond flux also around this undeformed point. And we know actually Berkowitz, Waffer, and Witten also give, as I said, how the PSU 1,1/2 Weissenmiller-Witten model gets deformed when you turn on Ramond-Ramond flux. So it turns out what happens is that in the Weissenmiller-Witten model, you have, and like in any Weissenmiller-Witten model, you have two terms, a kinetic term and a WZW term, and their coefficients have to agree. That's what defines the Weissenmiller-Witten model. But it turns out for these supergroups, you can still have a conformal theory if the coefficients are actually different. And so in a way, if you start with the Weissenmiller-Witten point, which corresponds to pure NS-NS flux, and you deform a little bit with RR flux, that changes the coefficients slightly between the kinetic term and the Weissenmiller-Witten term. So that's another deformation of the theory, which preserves the conformal invariance. And you can try to also include, see what happens when you turn that on infinitesimally, and try to compare that with something in the CFT, which is more interesting, which is also very interesting, I think, because it tells you how maybe you can treat the Ramond-Ramond flux perturbatively and try to deal with that. So yeah, so these are, I think, interesting questions which have not been explored. All right, so so let me now, if there are no further questions, let me talk about the matching. So this is in some ways really the part which is about deriving the correspondence, because so far I've sort of showed you how things agree with the spectrum, but in some sense the non-trivial part of the non-trivial part of the ADS safety correspondence is in the matching of the spectrum. So I want to just say a few words. What does it mean to derive some a particular example of the ADS CFT correspondence? One operational definition which we will adopt is the matching of the endpoint correlation functions in the Euclidean theory, for instance. So endpoint correlation function of the planar or the perturbative spectrum of operators on both sides. So in other words, if we can show the equality of the correlators without necessarily kind of necessarily getting so let me write this out. So this is what I operationally mean by deriving the correspondence, which is that so the left-hand side is the string theory. So so this is the what you would define in the, so this is the let's see, so this is the string theory. And this is the orbifold CFT, more generally, of course, any dual CFT. So what we have here is essentially that, so these are physical vertex operators of the string theory. The W's, of course, label the spectral flow. So for each physical state that I mentioned earlier, there is a vertex operator by the usual operator state correspondence. These H's refer to the space-time conformal dimension. This is the worldsheet position, the worldsheet coordinates. I will always denote worldsheet coordinates by Z, and the space-time coordinates in the dual space-time is we'll take to be a sphere. That's the boundary of the ADS3 where the CFT2 lives, and that we will denote by X's. And we'll consider, as I said, the endpoint function. This is the n-punctured sphere. This is the worldsheet. And this is, of course, the boundary S2. So there are two spheres. There's the worldsheet S2. So worldsheet, which we'll take to be an S2 because we are working in the planar perturbative limit. And the boundary is also an S2. And so X's label the coordinates of this boundary S2, that's X. And this is the worldsheet is also an S2, and I'll label that by Z. And so, okay, so, and this is the moduli space. The M0n is the moduli space of the n-punctured sphere. So this is what in string theory you're instructed to do. That so these are the single trace operators, also the single cycle operators. Okay. So the ADS CFT in general tells you that there is a dictionary which relates correlation functions in the dual string theory with correlation functions in the dual CFT. And this is the definition of the left-hand side is the definition of the correlation functions in this string theory because it's the usual one. You take n vertex operators and you integrate them over the moduli space. And I mean, the expectation value of those vertex operators. So you evaluate them in the worldsheet theory for fixed z's, and then you integrate over, in the case of the sphere endpoint function, you basically, this is, you can fix 3 of the coordinates and you integrate over the remaining n-3 coordinates. So this is n-3 complex dimensional moduli space. And the right-hand side is the usual correlation function that you would define in the orbifold CFT on where you're working on a sphere. And you'll be picking out the G equal to, yeah, so this is sort of suggesting that you're picking out the planar pieces, so to say, the pieces that correspond to the large n limit. Okay, is this clear? The all the terms in this equality. All right, so now, of course, when I wrote this, I was implicitly assuming that this, so this equality presumes a more basic correspondence, which is what we have, which is that between the vertex operators and the single cycle state. So this is the matching of the spectrum. So this presumes the matching of spectra. Yeah, which is what I was, that's why I spent so much time in explaining this. So there's to be a 1:1 correspondence. You have to tell which correlator corresponds to which vertex operator. So you have to have this correspondence, and that's what we had earlier. So, so we can build on this and now try to argue for this sort of matching. So we'll mostly focus on the case where the dual, from the point of view of the dual CFT, the operator is equal to what I'll call sigma W. Something wrong with my sigma W H naught. This is the ground state of the W twisted sector. So there's a twist field in the W twisted sector. And so the ground state, the H naught, has a very specific value in the W twisted sector. The H naught is W square minus 1 by 4W in this T4 theory. So we'll mostly focus on this case, and the corresponding dual string theory state will be the ground state of the W spectrally flowed sector, which corresponds to the ground state of the W spectrally flowed sector. So it's a bit like focusing on e to the ikx operators. So if you wish, I won't consider all the whole stringy tower of excitations, but if you see how it works for the ground states, then you can see how it can potentially generalize. There'll be just more kind of indices and other complications. But the least complicated thing is to match these ground state correlators. So that's what we will mostly focus on. So, okay, so this is our task, and what we will see is, so let me just mention what we will sort of what we will see in the following, so that you don't get lost in the technical details. So what we will use is, we'll of course again use the free field realization. of the of this PSU 1,1/2 theory, and we'll use word identities to constrain the correlators on the string side. So the string side is the left-hand side of this above equation that I showed. In fact, what we will see is that this correlator before integrating over moduli space has a very unusual property that it has delta function support at isolated points on this moduli space. So, so what are these points? These are the points Zi. So the Zi are labeling the moduli space. Remember, in this correlator, Z1 to Zn. Of course, you can fix 3 of them to 0, 1, and infinity, but yeah. So the points where it's localized are where the Zi, these are the points Zi such that there is a branched cover which I'll denote by gamma of Z, such that, so gamma of Z will be branch cover, so it's a map from the world sheet to the world sheet, which is labeled by Z, to the boundary S2 of the ADS3, where so it's a branch cover at the Zi's. So the gamma of Z is approximately in the vicinity of each of these Zi's. It takes the point Zi to the point Xi, but with a branching number W. So this is true for I equals to 1 to n. So if you have, this is what you would call a branch covering. Of the S2X by the world sheet with branching Wi at the location Zi. So these are the only branch points, and the so I claim that if we specify the branching data namely the Xi and the Wi. So supposing I tell you the points Xi, because Xi are things that are fixed by the boundary correlator, right? And the Wi are also data that are fixed. So supposing I specify this branching data that there are branch points Xi, so there's a branch cover such that the Xi are branch points with this behavior, branching Wi, then the covering is actually rigid. In that the n-3 zi's are fixed in terms of the branching data, namely the xi and the wi. So once I fix xi and wi, I actually don't have any freedom to choose the n-3 zi's. So that's what I meant by saying over here that these are the points which admit this branch covering. So supposing I tell you this data of this xi and wi, and that there is a branch covering of the sphere by the sphere, where these n are the only branch points, then it's not very difficult to argue this, and I can tell you later if you ask me after the lecture. I can tell you very briefly why that's true, but it's basically because this gamma of z is in this case some polynomial ratio of polynomials of degree n, with n is given by the so-called Riemann-Hurwitz formula. So so this gamma of z is fixed to be some polynomials, ratio of polynomials, with the degree of the polynomials being fixed in terms of the wi. And this is the underlying reason why it's very rigid. So the so what we will see is that the that the moduli, that the worldsheet correlator is localized to a discrete set of points. So it's proportional to something like I equal to 1 to n-3. So so this is quite unusual behavior for a worldsheet correlator to behave as some delta function, but this is what the free field ward identities will tell you, and this is what I will try to briefly sketch. It's also a signature of a topological string theory, and we have already seen like a couple of times other signatures of topological string theory. We know, I mean, various other A-model string theories and so on have this sort of similar property. So it's in that sense not unusual, and moreover, this will be exactly what the dual CFT correlator needs. So the dual CFT correlator will actually be written in terms of these covering maps, and I'll try to explain that also very briefly in the remaining time that we have.
I have one question about the verification. So is it all of them are Euclidean calculation, or this ADS side?
I'm focusing right now on Euclidean correlators. I haven't seriously thought about the Lorentzian continuation. I think that will be, one can try to work it out, but like in any two-dimensional CFT, I think the Euclidean correlators are the natural things to first consider, and then one can try to build a Lorentzian thing out of it that has more complexity, of course.
Yeah, CFP2, yeah, Euclidean is
Yeah.
I mean, one can think, but then should we consider the ADS side? Should
we
it be like
consider?
Euclidean? I mean, in ADS side, is it Euclidean? Should it be Euclidean ADS, or I mean,
Yeah,
this is just naive question. So
yeah, well, I mean, it depends. You can, so when we talked about the spectrum, we were in a sense working in thinking of Minkowskian signature. We were thinking of the Lorentzian ADS3. But when you compute correlation functions, once again, there's an underlying two-dimensional worldsheet CFT. So you can think of just computing correlators in that two-dimensional worldsheet CFT, which will give you sort of, which you can think of in the language of so you are working at a two-dimensional worldsheet, and the boundary will be parameterized by a sphere. So you will actually be working in so it's a little subtle with these free field variables. The difference between Lorentzian and Euclidean signature is in some reality conditions that you impose on the free fields. So the simplest one where things are related by some conjugation corresponds to Euclidean signature. So you can look at the same free field correlators in Euclidean signature or Lorentzian signature in spacetime. But Euclidean is easier again in the string theory point of view.
So there's something related to the here you in the first lecture you begin with the SL2R, but
Yeah.
If your target space is Euclidean ADS, then do you have to using the a SL2C or something like?
You can think of it as the three-dimensional ball, which is like SL2C mod SU2 or something like that. Yeah, so the hyperbolic space, the three-dimensional hyperboloid. So I think that's the implicitly, I think that's what we are assuming when we compute these correlation functions.
Okay. Yeah. Thank you.
This statement is valid also for non-zero tubed coupling?
Which statement about
this relation gamma z in terms of this delta function?
This in terms of this branch cover?
Yeah.
I think so. When you perturb it, I think the picture will be more complicated. So I don't think it will localize on the like this discrete set of points. It will get smeared out, I think. But that would be more complicated, I think, to figure out. But I think I can see that it will not remain any more localized. So this is very special to the free point.
I see. But if lambda tube-to coupling goes to infinite, the other limit.
Yes.
Then this is a very rigid string, right? Such that it's moving in the target space.
Yeah. So that's what when you go to lambda, as you increase lambda, the string becomes less and less rigid.
Yeah, and the other limit that if lambda is finally infinite, then string does not fluctuate at all, right? It's a strictly.
It becomes point-like. It becomes supergravity.
No, it can have a string also. It can be string.
Well, in the strict k goes to infinity limit, you go to the supergravity limit. So I'm taking k as some. It depends on what you. When you say large lambda, I was thinking of supergravity limit, but maybe you're thinking of something else.
Yeah, of course. For example, giant meganon is a well-defined.
Sure, you can think of string-like excitations, which are of very high energy. Yeah.
So you're considering the ground state, for example.
Yeah, I mean, here I'm working, of course, at k equals to 1, and I can consider all the states. So I'm considering all the states here when I'm talking about things. For that particular case of correlation functions, I will be focusing on the ground state, but this localization will be true for all the states.
Okay.
That's generally a feature, but it is true that this will be less and less localized. In fact, I think even turning on an infinitesimal perturbation will smear out these delta functions.
Okay, thank you.
So, sorry. Yeah, please.
Go ahead. Okay. So I just have a small question on this, the matching criteria that we discussed a little, I think in the previous slide. Could be just
the matching.
This one. Sorry, I think, yeah, after it's matching the correlation function. I think the next slide. I'm sorry.
Yeah.
Yes, this one. So we have this matching of spectra for the vertex operators of the string with the orbifold CFT operators, right? So does this also hold for if one includes black holes in the system? Like, this should not be the case for non-perturbative things.
Well, I mean, if you are considering a full non-perturbative, I think the strongest form of the ADS CFT correspondence is where there's an equality between all states, not just the perturbative states, but all states of the string theory with all states of the dual CFT. So, of course, if you consider a black hole state in this string theory, there are many microstates, and there will be a 1:1 correspondence between those microstates and the microstates and some highly excited states in the dual CFT. So you expect something like this, except that they will not be given by some perturbative string vertex operators like this, because that whole vertex world sheet picture will, for a finite coupling, is probably not the best picture to have for finite string coupling. But the statement about the correspondence between states, I think, will be true, that there will be a matching of the spectrum.
Okay, so what kind of operators do we have to expect in such a case of, if we say that there's...
I mean, we don't have a very good non-perturbative definition of string theory, so it's difficult to say, but perhaps something like a string field theory, there will be some physical vertex of physical fields in that string theory that you build out, some gauge invariant fields. But yeah, but it's still, I think, not something we have a very concrete way of thinking about it.
All right, thank you.
So I'm just wondering, this localized behavior, is it also true for higher genus Riemann surfaces?
Yes, so this was shown by Lawrence Eberhardt and Andrea, not Bob Knighton, in 2 separate papers. I mean, they went ahead and generalized what I'm saying, going to say now. They generalized it to higher genus Riemann surfaces also. So
then you can compute the left-hand side, I guess.
Even the left side for genus G, and you can compute you can just add G instead of 0 over here. G equals to 0 and 0. You can replace that by G. So that I'm just, for the sake of technical simplicity, I'm not talking about that, because then you have to talk about covering maps of Riemann surfaces which of higher genus, which is more complicated, but it has been done.
I see. Okay, thanks.
Okay. So so what we will do is we'll consider, as I said, the ground state. So in the string side, so we'll look at correlators. Of vertex operators that correspond to something like this M1, M2, spectrally flowed by W. So this is the I should maybe call it M1 tilde, M2 tilde, and because of the spectral flow. So and we'll denote these by VW. Okay. So this is what these states will be that we'll focus on, and our logic will be to use OPE to the OPE of the free field. So right now we are working on the string theory side, and I will try to connect it later with the dual CFT, but we will be in the string theory side. We remember we have this free field realization. We have these fields psi plus, psi minus, eta plus, eta minus, etc. So we'll constrain correlation functions of these sort of vertex operators by using the OPE of the free fields with these operators, and see what we can learn. So so as I suspected, since this already took some time, I wrote out the slides for this part so that we can go a little faster here, and I can try to complete this. So we can write the OPE of these free fields with these vertex operators. So so psi minus and psi plus, you can write down what their vertex, what their OPE is with this, because remember, these are these fields, and I told you in the previous lectures how psi minus acts on these were essentially labeling the so-called occupation numbers of psi plus, psi minus, etc., the zero modes. So you can work out the OPE, and you can see that psi minus sort of reduces M1 to M1 minus half, and psi plus increases M2 to M2 plus half, and there'll be a similar thing with eta minus and eta plus. But the information about the W spectrally flowed sectors comes in this part of the OPE. Because now, essentially, once you have spectrally flowed, then you have essentially shifted the mode numbers by Z to the W by 2. Remember, that's what the spectral flow acting on the free fields was shifting the modes by up or down by Z to the plus W by 2 or Z to the minus W by 2. And that's what this psi plus, psi minus, the different OPEs do that. So they take this particular form. So if Z and Z naught. So here I'm, for simplicity, considering where the x's are 0. You have to do some little bit of additional rotation of the vertex operators to take it to an arbitrary x position. You have to kind of translate it. But in any case, you have these psi minus, psi plus OPEs, which are like this, and this will be the basic ingredient, because one can, from these OPEs, derive an identity which will tell you in a way what the geometrical interpretation of these free fields are. So I just introduced them as free fields which generated this current algebra, like in SU2, but actually there is an interesting geometric interpretation of these free fields in terms of twistors. And this will become more apparent and more important when we look at the 4-dimensional case. In the 2-dimensional case, it will be still a little trivial, but it is an important precursor to the 4-dimensional case. Okay, so so the key thing will be to derive something which we call the Twistorial incidence relation. And the way we derive, so we derive a certain word identity of these correlators. So the way to do that is to first define these quantities P plus minus. So I will look at this product, this endpoint function of these correlation functions. Like I said, so these are the physical vertex operators. Now, because of this superstring theory, there are some analogs of what are called picture changing operators, but never mind that. You can just ignore this part right now. But for the correlation functions to be non-vanishing, you need this piece. So, but these won't play much of a role. You can write down similar OPEs of psi plus, psi minus with these Ws. So that's why we have put them here. They actually have zeros at simple zeros at when Z approaches U, and when Z approaches any of these Zi's, you have what I wrote down over here. So let's define this quantity. Namely, you take this correlator with psi plus minus and with these physical vertex operators, and you multiply by these factors, which are chosen carefully in a particular way. So this is Z minus Zi to the Wi plus 1 by 2, and these Z minus U, which is this position over here. So it turns out, so the reason these factors are chosen is that if you look at its dependence on the Z, on just the variable Z, it's a polynomial of degree, a specific degree in the Zs. And why is this? Because you see, this is designed to cancel the zeros that are there in the W's, and this factor essentially kind of compensates for the singular behavior that might be there when you have, say, psi plus acting on these vertex operator. This object doesn't have any poles, so that's the reason why we have sort of introduced this. So the poles are cancelled, and you can actually look at the degree, and you can argue from the meromorphic nature of the correlators that this is actually a polynomial. And the degree of the polynomial you can work out because it's essentially the degree of Z. I mean, you can again write down by going to infinity, where this, you know how this correlator behaves at infinity, and looking at the powers of Z, you can write down what it is, and it is the same thing that I wrote down earlier. It's given by this combination with this degree n. And so it's a polynomial of this degree. So these are two sets of polynomials for both the psi plus, psi minus. You get some p plus, p minus. So yeah,
here the polynomial, this psi plus and psi minus, they have different OP factor. In the previous slide, they have different.
Yeah, because one was spectrally flowed with plus W by 2, and the other was flowed by minus W by 2. You remember in the mode numbers, there was a shift. The psi minus had was shifted one way, and psi plus was shifted the other way. But they are both spin half. That's why you get a minus half. But then there's an additional factor of Z to the W by 2 and Z to the minus W by 2.
So, and then in the polynomial, you compensate the same factor. So
yeah,
is it no problem? Like, don't you have to also compensate the different factor, or here plus minus?
This is for all the W's, because these are all the possible poles. So in a CFT correlator, you know where the poles are. The poles are coming from the OPE, right? And this factor compensates for all the poles.
So you don't, I mean, it's okay to introduce a zeros. Only you don't want to like a pole. So zeros is okay.
Yeah, there might be some additional zeros that might be there, and yeah, I wanted to remove these zeros for because those are kind of a little spurious. The U's are kind of like picture changing operators; they are a little spurious, so this helps to remove those, and it plays a useful role. Yeah.
Okay, thank you.
So furthermore, actually, you can look at the X dependence and see that when I look at this combination near, as you approach any of the Z going to Zi, if I look at P minus plus Xi times P plus, so I didn't write it over here, but you can actually write down what the coefficient also is over here. So in fact, that turns out to be a relative kind of an Xi factor. And you can show that this P minus plus Xi P plus is proportional to Z minus, vanishes as Wi as a power of Z minus Zi to the power Wi as Z goes to Zi. So these P's, of course, have shown their dependence on Z, but they also have dependence on the Zi's and the Xi's, and that might take the form of and it will take the form of a distribution. So it turns out you can kind of pull out the distributional piece and just be left with some ordinary polynomial piece in the Z's. And these polynomials define a covering map by this expression. Supposing I have polynomials P plus and P minus, which are of degree n, I can define gamma, which is essentially the ratio of this P minus to P plus, and that's what I'm doing here. I'm defining a gamma of Z, which is given by this ratio. And so when you do that, then this tells you, this equality essentially tells you that as Z goes to Zi, the gamma goes to Xi and then plus this. So it is really a branch cover of order Wi. And as I said earlier, the covering maps, these covering maps with specified branch points exist only on a codimension n-3 subspace. These are a discrete set of points. So therefore what we have is an identity for these correlators, namely the psi minus plus gamma of Z psi plus is 0, because that's what essentially you can show that these polynomials by the definition that the psi minus plus gamma of Z, because essentially P plus P minus is D times this. So if I put this into this expression, you can see that by the definition, this combination of psi minus and psi plus has identically 0 with inside this correlator. So this is an example of a word identity that you have for these correlators in terms of gamma of Z, which is defined in terms of a covering map which has these properties. So once, in fact, like I said, if you specify these Xi and Wi, this branching data, you have a unique covering map, then basically that tells you what gamma of Z is, and you can compute this combination and show that it vanishes. And this is what we call a twistor relation, because I should say this maybe, but some of you may be familiar with twistors in 4 dimensions, where you have some kind of an incidence relation with X alpha dot. So this is a sort of generalized, this is a simplified version of these, and these mu's and lambdas are behaving like twistors. Mu's and lambdas are the twistors in 4 dimensions. So this is some kind of a two-dimensional version of that, because you remember this X alpha is essentially this covering map is a map from the world sheet to this thing. So you can think of gamma is a map. So gamma of Z, as I wrote earlier, takes is a map from sigma 0n to the S2 parameterized by X. So you can think of this as X of Z. So in the case of, so X of Z is mapped from the worldsheet to the target space, the boundary S2. And you can see that this is very similar to the Twistor relation. And this will become more important in similar Twistor relations will become more important in the ADS5 example that I will talk about. But at this stage, you can just think of this as a name. So in any case, the localization of the correlator on this codimension subspace follows from this, because now you can write, if you put this back into this, use the fact that gamma of Z is like this and use these definition, you can, what you learn is that the D times this combination is 0, and therefore D is a sum of products of delta functions, because the only solution to X f of X equal to 0 is when, so you have something like X times f of X is 0 is only when f of X is proportional to delta function of X. So if f is non-zero, of course. So D is sum of these delta functions. And in fact, the Twistor relation constrains the correlator even more. And you can show that the correlator has to not only have these delta functions, but also the coefficients depend on the, I didn't write this, I guess, over here. The AI gammas are effectively the coefficients that appear over here. So the thing that multiplies Z minus, so this is, I can write it as AI gamma. So AI gamma are these coefficients. So that depends on the xi's and the wi's in some complicated way. And you can show that that's what enters here times some overall prefactor. There's another argument which I don't have time to go into, which uses a semi-classically exact solution, which tells you that this W gamma factor over here is proportional to a Liouville action evaluated on a Liouville field, which is log of mod del gamma square. And this will connect to something that I will mention in the symmetric orbifold due to Lund and Mathur. But this semi-classical solution is something we had found in the paper, paper with Lawrence, etc. And you can show that this piece is also constrained. And in fact, this whole thing matches exactly with the correlation function of the orbifold. So I will, I'll explain that, but first let me say a couple of words. Yeah, I think I'd said it here, that the Twistorial relation, because this is the analog of the Twistor relations, these are also sort of, these are the spinors. And in fact, the you can write down a free field action for our fields. As I said, there are free fields, and it's exactly like the Berkowitz's action. He wrote down an open string action for these super Young mills, but it's based on, if you combine these size as one set of fields Zi and the other etas and chis, bosons and fermions in another Twistor field, Zi, then the free field action, the one that I wrote down earlier, where etas were conjugate to psi's, you can write them free field action exactly like this, and together with a gauge field, which imposes the constraint that which takes u1,1/2 to PSU 1,1/2. So that's the, so if you look at the current which couples to A, it's essentially the U1 current which you gauge out by. So this is exactly the twistorial kind of action that was there in 4D Yang-Mills, which was in terms of PSU 2,2/4 super twistor variables, but we are working sort of with half of them, the PSU 1,1/2. But next seminar, when I give the seminar, I will describe how for the 4D Yang-Mills, it's based on essentially very similar set of free field variables, but now involving these PSU 2,2/4 twistor variables. So this will be the sort of link between the 3D and the ADS3 and the ADS5 case. So I'm just putting it for that reason. But coming back to the symmetric orbifold, this, as I said, in the matching of the correlators, this this is, I very briefly sketched for you what the correlator, the physical correlator of the string theory will look like, that it's product of delta functions, and then it has, so it has this product of delta functions. There's some complicated dependence on x's and w's, and then there's a piece which also depends on the this covering map through this Liouville type of action with a Liouville factor proportional to this. So this is what you get from the world sheet analysis. And very surprisingly, this is exactly what the symmetric orbifold also gives. And why is that? There's an old observation due to Lunin and Mathur that that you can compute the correlator in an orbifold, symmetric orbifold, by going to a covering space. So remember what I said, when you have a W twisted sector, you can think of the T4 fields as being permuted by a sort of a W cycle inside the symmetric group. And this permutation means that locally you can go to a branched cover. So what Lunin and Mathur introduced was from the X space, they introduced a branch cover Z to the W such that the fields are single valued on that branch space. It is maybe something people who have worked with Renyi entropy and so on know this, that when you have a twist field, you can go to the covering space and then the fields become single valued on that covering space. So here, when you have a W cycle twist, you can go to a W fold covering space, which is locally like X is Z to the W. And this you can do at each of the insertions of your correlator. Each of one, you have W1, W2, Wn. So locally you have these branch covers, and globally they patch together to form some covering space, which is, I mean, I should have drawn it, but it would be like there would be some covering spaces with so you can think of this as my world sheet sigma, and this is my boundary S2, and these are branch points. So you have Xi, and that's lifted to some Zi. This is something. These are all Xj, Xk. These are all different branch points, and this is a branch cover. And you're lifting from your S2 to this multi-sheeted cover. And these sheets, of course, have to combine together to form the world sheet. So they talked about a covering space, but what we now see is that that covering space is exactly the is exactly this world sheet. So we'll focus on these twisted sector ground states, like I said earlier. So they gave a very clever way to, Lunen and Mathur gave this clever way to evaluate the orbifold correlator. And by going to this covering space, what they said is that now when you consider the ground state in the covering space, of course, fields are single valued, so there's no twist. So it's like inserting a vacuum operator in the covering space. It's like a vacuum insertion in the covering space, but now the covering space is a Riemann surface. So what instead of computing the correlation function in my original space, I can go to the covering space and compute the vacuum path integral. But in doing so, you have like this pullback, right? I mean, so there is this here, this is the map gamma. Gamma is the branch cover, so you have a pullback from. If you had a flat metric in my original CFT on the S2, then when I pull back, there's a warp factor which is precisely mod del gamma square, because this is the pullback. D2x is d gamma square times d2z. Remember, d gamma is just dx by dz. And so there's a warp factor like this. There is a sort of a conformal factor, and so you get an additional Liouville term when you're evaluating the path integral. So you're evaluating the path integral on not just the original metric, but on this modified metric. And so you get the additional factor gives you a Liouville factor. And that Liouville factor is essentially this, which you have to regularize appropriately. And then you can argue that factor and then these normalizations, they give you some other factors like this. And these are exactly what, in fact, these AI gammas are. And so you get exactly what the free field ward identities and the classical solution gives you on the worldsheet side. So this was, of course, very sketchy and quick. You may not have followed all the details, but what I want to emphasize is that there's a structural equality between the two sides, that the structure of the correlators of the symmetric orbifold, which was given already by Lunen and Mathur more than, I don't know, 15 years ago, that agrees exactly with the worldsheet correlators. So once you integrate, so what we learned from the worldsheet correlators is that you get these delta functions, that it has this delta function support. But now when you integrate this, that means you'll get just the contributions precisely from these localized delta functions once you integrate this over the moduli space. So both sides, we have to now integrate over the moduli space. So then this delta function will go away, and you'll be left with essentially this part, which is what what you get here in the symmetric orbifold correlator. So the two sides are really matching structurally, and so it's so that's in a way how I think of the derivation of the ADS-CFT should go in general, that you make the two sides manifestly agree. It's not a question of checking the two sides and seeing if they agree case by case or this thing. You want to really see that they are structurally the same. That's what you would mean by showing that this side is equal to that side, so that you get an insight into how exactly the two sides are matching. So that's, I think, what this thing achieves with the correlators. And yeah, so that's, I think, more or less what I wanted to say as far as the ADS3 CFT2 goes. I mean, there was yet in the beginning of the lectures, I think I had two more topics, but I think those will be difficult to cover. I mentioned already something about the black holes in the tensionless limit. but there was also in my outline of the lectures, I think I had also put in another interesting thing that we had, and this is about going from the field theory to the string theory and matching this. So here I kind of focused on this part about the going from the strings to the fields, but there's a very nice way in which you can connect with some of my old work on how exactly field theories, Feynman diagrams and field theories reassemble themselves into string worldsheets, and these two kind of very much support each other. But that you can find the details of that in this paper over here. It's quite elementary and has some very interesting connections to the Schwartzian action for the that in some ways that Liouville action can be viewed as some kind of a Schwartzian action in some appropriate limit. So it seems to be some kind of a generalization of the Schwartzian action that you see in ADS2 to the ADS3 case as well. So, but there are many other things like this, which I don't have time to now get into, but I would encourage people to look if they're interested in some of these original papers. So with that, let me close. I've gone a bit over time today also, but I'm happy to take any further questions.
Thank you very much for a very nice talk. And please ask the questions.
So I have a question.
Yeah.
I'm not sure whether you have mentioned this as I missed your first lecture, but so I think there's an older paper talking about this taking this tension is k = 1 as a transition point. Something like realize this black hole and the string is transition. And somehow you mentioned this k is an integer, right?
Yeah, k is integer in this supersymmetric case that we are considering because it is quantized in the SU2 level is quantized, which means that this level is also quantized. The SL2R level is the same as the SU2 level, or more microscopically, the K is the number of units of Never-Schwarz flux. So that's quantized, yeah. So in this case, it's not possible to somehow take K greater than 1 to K less than 1 continuously.
Okay, so I guess there's a two definition of this K somehow. So in there's older paper, I can't remember the authors, but somehow they take.
If you just look at the bosonic SL2R level K, you can, the K is continuous there because there's nothing to fix it to be integer.
Oh, I see.
But here, because the SL2R is level K is combined with the SU2 level K. So therefore, the two Ks have to be the same. And since SU2 is integer quantized, therefore SL2 also becomes integer.
I see, right. Okay, thanks.
So other question? I have two questions. The first one is that you in the previous paper you talk about the relation between the OB4 and higher spin, but in this ADS string, could you make some comment on this higher spin? And is it some kind of proof of the tensionless limit of string is a higher spin or?
Yeah, no, that's something very, I think. It needs to be explored much more. So I can say the following. Some years ago with Matthias, we had around 2014-15 studied the properties of the symmetric orbifold CFT as a candidate tensionless limit, which of course is now we know what it corresponds to. But at that time we just viewed it from the point of the orbifold like we do for free angles. And what we realized is that, in fact, there is a very large higher spin algebra. Just if you view it from the point of view of symmetric orbifold, there is a very large higher spin algebra, which is bigger than the W infinity algebras. In fact, what we called it higher spin square, because effectively it's like a squared version of the higher spin symmetry. So it seemed as if like the whole untwisted sector was, in terms of this higher spin symmetry, it was like the minimal representation. It's a bit like the scalar that you have in the higher spin symmetry. You have all the higher spin fields, and then there's one scalar field which is in a very special representation of the higher spin symmetry. So we found that the whole untwisted sector, which is actually many representations of the Virasoro or even any single W infinity algebra, but becomes one representation, this minimal representation of this. But then there are all these W twisted sectors, which are also some complicated representations. And but nevertheless, it seemed as if you should be able to view the string theory as, I mean, at that time, we didn't know what the dual string theory was, but from the structure of the symmetric orbifold, it seemed as if whatever the dual string theory is, it should be viewed as something which has this big higher spin symmetry, this enhanced higher spin symmetry, spin square, coupled to some discrete number of matter fields. So the whole string theory could be viewed as a higher spin theory. Now we, of course, understand the dual string theory side, and we know where the higher spin fields are coming from, which sector it is coming from in the dual string theory. So it should be possible to understand this better from that point of view and see how to organize the string states into higher spin multiplets. In terms of this even bigger higher spin square. And in our most recent paper, we have a section on ADS3 where we have some comments, some preliminary discussion in that direction. But I think in general, this is something which can now be explored, I think, much more fruitfully. To what extent is string theory like a higher spin theory, and to what extent it is not. So on.
I see. Okay.
And similarly for the ADS5 case also, I think now we should hopefully soon be at a similar stage for the ADS5 string theory dual to free Youngers.
And
you can ask then other questions, just like how do you Higgs this symmetry? How is this symmetry going to get Higgs? And as you move away from this orbifold point, etc. So I think there are many questions one can ask in this direction.
Yeah, so I also have other question, but it might be a little bit exactly late to this lecture, but in the past there was a paper like this by reporting some CFT, you cannot make some holographic shift or something like I forgot.
Sorry, I didn't understand. Can you say that?
There is just like a study of the holographic CFT by using the reporting reporting. So like I think Felix Haya or several people, right? So
you by orbifolding,
any like you consider any like a seed CFT and the by using orbifolding.
Yeah, so not all orbifolds. There are a class of permutation orbifolds and so on, which you have to have certain kind of, you have to have a to get a Fock space of states. I think you need it must be some subgroup of the symmetric group which satisfies some conditions, I think. some various people had papers on that. But the dual CFT, the dual string theories were never identified. So I think there are many candidate dual CFTs which can have string duals. There are also many string backgrounds which can have candidate CFT duals, but this matching has not been done, because I think Jerome Gauntlet and many other collaborators have worked out large classes of ADS3 backgrounds which have lesser supersymmetry, but nevertheless can be given by some D-brain constructions, etc. But what kind of dual CFTs they have, no one knows. And at the same time, on the other side, also there are large zoo of potential dual CFTs that you can have. But yes, I think it is a kind of a dating problem to find the match between the two.
I see. So this is the one example for this duality, concrete example for this duality.
Yeah.
Is there any other example?
I mean, there is, of course, a K3. You can, what I said, you can generalize to K3. There is also the other maximally supersymmetric background is ADS3 times S3 times S3 times S1. And it has what is called large n equals to 4 supersymmetry. And there was some proposal some years ago for a dual to that in terms of a symmetric orbifold, but it's a more complicated symmetric orbifold, and there is some evidence for it, and maybe that is another case that can work more immediately, which will be somewhat different from the T4 and K3 cases. And then, of course, one can try to go with lesser supersymmetry, but I think this is sort of the cases. One would have to probably start reducing supersymmetries in some way, and maybe take orbifolds of this, which will probably be leading to some of these other zoo of CFTs. But I haven't thought very seriously about these other cases.
Without supersymmetry, is it also impossible to find such a relation? Because you showed a very nice relation between this non-supersymmetry like orbifold and the highest duality between the highest spin, right? So,
yeah, you mean the WN minimal models and so on.
Yes, exactly.
So I think there should be. I mean, there should be some this thing, and I think this is. So I think we just don't understand enough the space of all the string theories that you can build from these sort of free field realizations and so on. I think there are many more. If we start from these free field realizations, I think we can build many more string theories on ADS3 and perhaps some non-supersymmetric ones as well. So this is my hope even for ADS5, that we have to, if we start thinking in terms of the large radius limit, then we are always kind of stuck to the supersymmetric cases. But I think if we start from small radius, then we can think of other possible backgrounds. Because it's more non-geometric, but that's also an advantage because you can consider different CFTs, which are non-geometric CFTs or not simple geometric CFTs, but which are non-supersymmetric and yet critical, and maybe they don't have tachyons and other problems.
Okay, I see. Thank you very much for your answer. So any other question?
So actually, I have a small question. Oh, yeah. Go ahead.
Sorry, just go ahead.
Yeah, please, yeah. Oh, okay, maybe, yeah, please, yeah.
Okay, so for this, I just have a question on this putting black holes into the system. So you mentioned during the talk that, instead of considering this D1, D5 brain system, one will have a canonical ensemble of states because there are really many microstates for the black holes. Yeah. But still, I wouldn't think of a black hole as just a statistical system, right? It's quite different from considering a canonical ensemble of states and thinking of that to be a black hole, right?
But just explain how you would want to view it. I mean,
Because,
in the sense that when you think of the black holes as having a temperature and so on, then you are thinking in a canonical ensemble, right?
Yeah, sure. But interior of the black hole does have some, of course, many microstates, and whatever goes inside this singularity, we just don't, we cannot just consider that as, a piece of coal or something like that, right? It's
right. So there are, of course, because of the large number of microstates, I think there are many questions about the thermalization scales and other things, which, yeah. So, I mean, I don't have any insight to give on that any further this thing. And but maybe in this example, by looking at those states, one might be able to say some things at least. I don't know how. But it is in a very highly stringy regime, so it's very far from our normal geometric intuition of the polarities and horizons and so on. So how these are connected is an interesting question, and how much things go smoothly from one description at large curvature to small curvature.
Right. Thank you. Thanks for the nice talk.
Thank you.
Okay, I just have a small question.
Sure.
So in the talk, you mentioned several times the similarity to topological strings.
Yes.
But this is very different from this ordinary topological string where you mix the spin with the arch origins. You have A and B twists.
Yeah.
Right?
Well, yeah. I mean, I don't know what it will. It's not a standard. I don't think it's a very simple standard topological string, but it is sort of. I mean, the spectral flow, I think, introduces something like the twist, because you are. It's not by some R symmetry, but you're kind of shifting the mode numbers once again, which is like shifting the conformal weights. But
this would make the theory topological.
I don't know. I mean, I wish I could answer better, but I think it's an interesting question. I'm not very sure. I mean, we are trying to figure out what kind of, but it's not going to be, I think, a very standard topological string. It will be slightly new, but it's closer in spirit to an A model topological string, because many places you see only holomorphic maps appear, and the kind of localization that happens is very similar to what happens for the A model topological strings. So in some ways it's close to A model, but probably also different.
I see. Okay.
Okay. Yeah, but I can't at this stage. I don't know better how to say it.
Yeah. Thanks.
So any other question? If not, let's thanks for the great street lecture.